Boom. All right. Cool. Very excited about today. Excited about every day in differential equations. Who wouldn't be? I won't look up to see the answer. All right. Let's just take a minute to come into the room. Overtone is forming in there. It's still there. Wow, that's so cool. All right. I should just let it go, but we're rolling on. Anything I can do for you all? Questions, things you need to talk about? There is 2 homework problems out and about, D fields. You probably didn't know about that unless you watched some version of the lecture. Did I actually put them in the second lecture? I'm starting to wonder who. I know some people watched that. I'm assuming it was people from here, but it might be just like random. Who watched the one that was all just whiteboard? No one?
Some of us were there.
Yeah, but 6 people watched it. Okay, whatever. Yeah, it's all good. It's all good. So I gave a couple of problems to sketch the D fields for. How is that going? Going okay? Cool. Highly recommend. So even though you were there, Lou, I would still recommend watching the redone version because I think explain a few things differently, and I think they make the process better. And in fact, let's do a warm-up, shall we? Let's do a relationship before we get into some like physics and chemistry and stuff. We're gonna do a mixing problem, and let's start off with something chill. So, there's this couple of folks, R and J, back at it again. And R has, remember now, this is the velocity of love. And this is the velocity of R's love towards J. So this reflects the person R's feelings about J. If R is positive, that's love. The greater the magnitude, the greater the love. If R is negative, that is not love. The opposite, whatever that is to you, dislove. I don't want to say the H word today.
Contempt.
What is that?
Contempt.
Contempt. Oh, I like that. The greater the magnitude of a negative R, the more contemptuous R feels toward J, and then J's feelings toward R are governed by J plus R. Let's understand this relationship, and let's use some of the techniques we talked about together to do so. So what's step 1? Somebody help me out. If I'm doing this by hand. So step 1, if I'm doing this with the computer, is enter it in the computer. That's easy. Oh, go ahead, Evan, and then I'll trace a note.
I was going to say find like the no planes.
Find the nullclines. Yeah. Step 1, sketch the nullclines. Is that what you were going to say, Tracy?
Yeah.
Cool. Beautiful. Step 1, sketch the nullclines. And Tracy, could you, since you were going to, what are those what does that mean?
Setting them to 0.
Yeah, setting the rates of change equal to 0. So the nullclines, we're going to have an R dot equals 0, and we're going to have a J dot equals 0. And we're trying to find where those rates of change are completely 0. Where R dot, well, it depends on how we set the axes up. I guess I'm going to make R the horizontal axes, just because I'm doing the XY thing, and oops, and that's how our brains work. I think I'm recording. So Daniela, you got it. Thank you. So if R dot equals 0, that means there's no change in the horizontal component. So there's only pure vertical change. So this is pure vertical change. And then this, where J dot is equal to 0, says we have pure horizontal change because there's no vertical component. So here we're going to have arrows like this, or this, and then down here we're going to have arrows, arrows that go pure up or down, and then down here, one of those two, along those curves where this happens. So R dot equals 0 when negative R equals 0. And negative R equals 0 is the J-axis. So all along here, all along the J-axis, and I'm going to dot it just to highlight it, and I'll mark down here, this is where R dot equals 0, so we have up or down arrows. But this is a nullcline right here. And then the other nullcline when J dot is 0 happens when J plus R equals 0. So this is equal to J plus R. And that one I'm going to rewrite, so that just means that J is equal to negative R. And that's a perfect diagonal down and to the right. So let's do a little dotted line for this, and this is the J nullcline, J dot nullcline. Anytime we cross this one, if we cross it, we have a purely vertical tangent. Anytime we cross this one, we will have a purely horizontal tangent, because this is where there's no vertical component. So all along here, this one's a little easy. I'm just going to put some horizontal lines parallel with the R-axis to help me just remember that. And I'm not going to do it here. It already kind of looks like they're there, but I need to eventually assign arrows. So far, so good? Cool. All right. So now, step 2 is to find any equilibrium. Cormac, where would that be?
0, 0.
0, 0. And how are you discerning that? That's 100% right.
Just where the two nullclines intersect.
Yeah, so exactly. So any place the nullclines intersect is an equilibrium solution, because both these rates of change are dead simultaneously. So here, it's just only at 0, 0. That will change in a few weeks. All right, so we've got an equilibrium right here. I'll just put a little open circle on it just to kind of note that. Cool. So here's where things started getting a little funky last Wednesday in class. So I want to say this all again and show you how to use the information more effectively. So that's step 2. Step 3 is test the sign of x dot and y dot in the regions between the nullclines. We know where those rates are 0. It's exactly on those curves, so it's non-zero everywhere else. To do that, just grab a couple of points. That says Twix. There, feeling saucy today. So let's say, for example, here at R is 1 and J is 1, make a little we'll just make a little chart, point, x dot, and y dot. All I care about is positivity or negativity of this.
Wait,
Oh, sorry,
did
thanks.
you just say
Yep.
what twixt means?
Between.
Between, okay.
Between. Yeah, I think it's a real word, Lou. Betwixt. Yeah. In between. It sure would have been faster to just write that, wouldn't it? Just literally spent about a minute there talking about it. So anyway, it's all good. So at the point, r equals 1, j equals 1, clearly in this region, r dot is -1, and j dot is the sum of the components, so positive. So this is negative, and this is positive. Again, I don't care about the actual values. So that means we have a leftward component and an upward component. So right here, and let's actually just make a little note here. We have r dot is less than 0 and j dot is greater than 0. So my arrows are left and up. That's the general flavor of them. If you catch any errors while I'm doing this, for the love of God, stop me immediately and help me. I'm an old man. Yes, Cormac.
Once you have that, is that enough information to say that the J nullcline, the top half, has upward flow?
100%.
Okay.
Yeah, actually 100%. So we are on, so here's where j dot equals 0. All along this line, right? J dot equals 0. If I know j dot is positive in this half, it must actually be negative in this entire lower half down here. The dots, the rates of change will change sign as generally as you pass over a nullcline. For a couple of weeks, that's going to be true. So over here in this whole little region, if j dot is positive in this whole region, in fact, I know that j dot is positive here, j dot is positive here, j dot is positive, negative in this lower half. So let's just go ahead and do that. J dot is negative, j dot is negative, and j dot is negative there. This isn't even actually a separator, but I'm just kind of putting it there again. Right, keep in mind, there's only really 2 separators. Let's put them in red. Or whatever that color is. Those are the only separators. So maybe I'll even take that out so that it doesn't look like I'm implying otherwise. Cool, and so now, check this out. R dot is negative on the right side of this nullcline where r dot equals 0. So that means r dot is negative in this whole right half. So again, down here, r dot is negative. R dot is positive over here. And we could finish that up, but that's a way to organize your thoughts. But once we get good at it, we can get quicker with it. Let me stop and help. Is there any confusion happening here as to what I'm doing? See a nose. Cool. All right. Cool. So now, like Cormac said, on this nullcline, since j dot is positive in this whole region, I know that this is an upward flow. That those arrows point straight up along that line. And down here, j dot is negative, so we have a downward flow on this nullcline. Nice. And then on the other nullcline, and so I highly recommend getting the nullcline signs. Sketch the nullcline directions based off step 3. Oh my God, did I say step 6 there? That's 3 or 4. Based on the 3 info. So that means here, r dot is negative in this whole right half plane, so these arrows on this null line have to point left. And over here, r dot is positive, so these must point to the right. And then here's the little detail that will make this all go so much better. These fields will change continuously. So in other words, the arrows aren't like this and then instantly like this. Everything changes gradually as you move around. There's never sudden jumps in arrow direction. And I can use that to my benefit because, for example, in here, I can get rid of that. I know that I have an upward flow and a rightward flow. And as I move from here to here, that flow needs to become horizontal. So here, as I move away from this, and let's see, yeah, so notice that is still upward and rightward. But as I move a little bit away from that, it's still going to be mostly vertical, but more horizontal as I get closer to this. And the closer I get to that leftward, purely horizontal flow, the arrows are going to chill out and become level. So I can use that to get a rough sense of what the flow is doing in here. And instantly, it's already better than anything I did last Wednesday. Let's, hey, could you take a minute and just kind of fill in the rest of the flow? Let's come back together. And just use those null clines as your guidelines. The closer you are to a null cline, the more the behavior's like that null cline. You're good. Okay. Good. Really good. Excuse me, sir. Thank you. That's great. Oh, you're bold. What a bold. You got it though. You're actually getting it quite right. Yeah. So these maximums will actually occur right on that line, just for like a subtle detail. You're getting the basic flow right. But see how the max of that curve is like right over there? The maxes should occur right on that line. It's just a subtle difference. Does that make sense?
Yeah.
But otherwise, you got the right idea. 100%. Looking stunning. Yes. Let's see. So, yeah, that looks, yeah, great. Good stuff. Yes. Are you catching up? You weren't here on Wednesday, right?
No.
You okay?
Yeah.
Okay. Okay, great. Smart. Yeah. Looking good. Looking lovely. Looking lovely.
Yes, here, do I come down, right?
Yeah. So they're going to rotate like that. As you, yep. Exactly. And your maximum for this curve is going to occur right on that line. You have a horizontal tangent, so the max will occur right as you cross that line.
And then you come back.
Mm-hmm. Yeah, exactly. Yeah.
It's kind of a map.
It's yeah. I wouldn't say that. There's could be more refinement added, but it's got the basics there.
Yeah.
Absolutely.
Oh, you can't decipher mine. Mine's
No, you're right.
Yeah.
You're absolutely right. You know yourself quite well.
Pretty good at squeezy.
Yes, it can get a little squeezy. I'll start adding in some arrows here. So then, once you get this going, draw some trajectories and see if you can make up a story about this relationship. there's lots of actual outcomes for this relationship. What are those outcomes? What are the possible places these folks could end as the sun burns out? Whoop. Keep in mind my guidelines. I'm going to start up here. So when I asked that question about what are the outcomes, pick a starting place in the plane of love. This is the plane of love. The first quadrant, good times for everybody. Both people are in love. The further out you get, the more intoxicating the love becomes. In this quadrant, stuff is pretty good for Jay. Jay is not feeling so hot. Or R is not feeling so hot about J, because R is negative here. Down here, this is the hell realms, my friend. This is like Shitsville down here. And you know, it's inevitable to end up down here at some point in one's life. If you're trying to find love, it doesn't always happen right away. There's a lot of trial and error in the process. I got a pretty decent flow there. Is this looking good? We got some flow. Yeah. So let's hear. I'll tell some stories. I don't know what your story. Maybe someone could tell me. Or let's. Where are some precarious locations for this relationship where things could go great, but man, if one thing's bad, somebody sees like a piece of food on the other person's face and they're like, gross, I'm out. Where are some precarious locales to be? Sensitive locales. Not emotionally sensitive, but like sensitive to disturbance. How about like right here? Yeah, right? Right about there, things, who knows what's going to happen. If I'm just a little bit south of a certain point, and what is that? That's northwest. Going to see that. What does that say? What does the relationship look like on this trajectory? Somebody just tell us a little story. Katrina, what's the story here?
They're breaking up.
Yeah, so where did they start? What was going on at this point?
It looks like they were, well, let's see. R was alright, I think.
So R's negative over here. So R's feeling a little contemptuous.
Yeah, and then J's okay. But
Yeah.
then things start taking a turn for the worse. And then they both end up hating each other a lot, and they're throwing things, and then
Yeah, throwing
Maybe.
things is about right here.
Yeah.
Yeah,
Throwing things?
it happens. Not at each other, hopefully. Somebody always punches a wall or something, or smashes some shit that the other person cherishes.
Oh, that's
Always?
Always.
Always.
They throw the passport into the lake.
Yes, exactly. Yeah. Oh, yeah.
It's diabolical.
I know.
But check this out.
What
Like
kind of
our kind of
relationships
fizzles.
are
Our fizzles out. At the end of this, R is just like, I don't give a fuck anymore. I'm done. Because the R is getting close to complete. What do you call it when you have no
Dismay.
feeling? What is it?
Dismay.
Not dismay, like lack of any feeling.
Apathy.
What?
Emotionless.
Emotionless, numb, over it. So ours feelings are dying out, and ours just like whatever. Meanwhile, R is getting a restraining order against J because J is getting a little psychotically angry, and it doesn't seem to be ending. So this is a pretty bad scenario for both of them. No one should be so miserable. And no one should have to deal with such a miserable person. Over here, and then up here, but if things had been just a little bit different, if that food hadn't fallen just the way it did, what do we got here? Somebody else tell me, what's the story?
Another restraining order.
Another, yeah, but for a different kind, right? Yeah.
Calming.
So this is the obsession. This is Fatal Attraction. Anybody ever seen that movie? It's like an old classic with Glenn Close. And, this is, I don't know which one that is, but this is where someone is obsessed and the other one's over it. Either way, we're feeling for R. Because R just really wants out. J is, needing some therapy, needing to work through some things. Down here, kind of the same thing. If we start down here at just the right spot, we end up in the same thing, except, honestly, this is pretty much the same thing, right? Over here, R feels a little of contempt that's always lingering, a residual contempt. Over here, there's residual love. But J is just J is just freaking losing it in almost every scenario. Except two scenarios. And we'll get to these today, I think. We'll find out. There is a very fine line that takes us to equilibrium. And it's got to be between these two, right? It makes sense that it would have to be between these two. So there's a fine line that if everything's just right, the whole relationship just fizzles. And everybody's done with it. And that, honestly, for this scenario, we pray for them to find that manifold that lies within their plane of love. So anyway, I hope, ridiculous stories aside, I hope that the method of sketching here makes a little bit more sense than it did last week. All right, cool. So any questions on this? Yes, Lou.
The vertical line, the J-axis.
Oh,
would
that's-
that be
yeah.
ultimate unconditional support and satisfaction?
That's a great point. So on this line, I forgot that this was also another place where we had a very clear delineation or just a clear line of action. This is, R was never feeling it. J spotted R across the quad.
This is you.
And fell hopelessly in love and just kept getting more and more in love. But R seems pretty oblivious and not interested. This is J just getting more and more in love. That's way better. Not for J. J needs help. J just needs help in all these circumstances. Like just a good friend and some time to heal. But this one down here is super bad.
Is there like a win-win scenario here?
They never met. Right, at equilibrium. I would say that's, just like ships in the night. That's as far as I can see here, Lou,
That's
that's
unsatisfying.
what?
Unsatisfying.
Well,
Sometimes like this.
yeah, so listen to the lady. Yeah, sometimes shit don't work out.
You did, man.
I'll tell you what,
Let's have an
next
answer.
time we do this, I will come up with a happy scenario, or at least one where happiness could happen. Sound okay? Deal?
Sure.
Okay, thanks. Let's do it. Let's do another example. I want to do an example. I want to derive some stuff. This one's a chemistry thing, not even close to my forte. The good thing with knowing math is you can figure out lots of things just by looking at the equations, even if you don't understand the ideas. Let's do an example and then use this as a stepping stone into what comes next. Very, very interesting, very cool example, even for a non-chemist. Mixing. So a mixing problem. And this is one of the places where systems of differential equations really plays a strong role. We've got a couple of tanks of solution. So it's basically a saline solution in this one. We've got fresh water pumping into this one. I better get my rates. I'm not going to try to even pretend to have memorized those properly. So we've got fresh water, fresh H2O coming in to this tank at 500 liters an hour per hour. So that's an inflow to that tank. This is a 300 liter tank, so it definitely would fill with under an hour, 3/5 of an hour. But we're gonna assume it's full to start with. We're gonna call this tank A. And I'll just write these things out so it's clear. Tank A contains 300 liters of water, pure water, and 100 grams of salt. Now I guess there's lots of kinds of salts, right? Chemistry people, salt is a general term. Is that true? Yes, cool, thank you. Salt is a general term. So whatever your favorite salt is, that's what's getting mixed into here. There's a second tank, tank B, right over here. Tank B is also a 300 liter tank, and it contains 300 liters of pure water. So tank B contains 300 liters of pure water. And there's a connector. There's an outflow and an inflow between these two. So there's this pipe that runs between them. And this pipe is sending 900 liters per hour from A to B. And there's a second one moving in the opposite direction. And this pipe is pumping 400 liters per hour in from B to A. And then there is an output. This is getting very complicated. There's an outlet here, and coming out of that is whatever this mixture is at 500 liters per hour. I think I'm using little L's and capital L's, but I really just mean liters. So 500 liters per hour pure water coming in, 500 liters per hour of a mix coming out. We want to understand the concentrations in both tanks at any instant. That sounds hard. This sounds hard. My brain doesn't work like this. But once we turn it into math, it'll start to make some sense. Everybody cool on the setup? Feel good? Awesome. Yep. Cool. So let's let X at T equal the grams of salt in tank A at time T, and Y of T is going to equal grams of salt in tank B at time T. And so I've got these initial conditions that I stated, but let's make them official. X at 0 is 100 and Y at 0 is 0. We're going to be able to analyze this completely and understand what equilibrium state is, how do we get there, what are the routes to getting there, and various concentrations. So we are going to make some differential equations. So X dot, this is the change in the grams of salt in tank A per hour. So this is grams salt per hour. This is a rate. Grams of salt per hour. So let's first off say that the concentration of salt in that first tank, what it equals here, is X at time t divided by the 300. That 300 liters is going to stay constant through the whole time. So this is the concentration of salt. This is grams per liter in A at time t. I'm suppressing the t, but we know there's an of t there. We know there's an of t here. And that is, let's see, hold on, I got to cheat. I tried practicing this, but I had to cheat again. What is it? Oh, 900. So that is leaving, so that is what's traveling through this tube. That concentration is what's traveling through this tube at 900 liters an hour. So we're losing that amount at a rate of 900 liters per hour. So this, let's get some units in here. This is liters per hour. And if you notice then that units cancel and we get grams per hour out of that. But tank A is changing because we've got this weird mix coming in that we don't really understand. But from tank B, we're going to have salt being added at some ratio. So we're going to have plus Y over 300. So this again, this is the grams per liter of salt in B. And that's flowing directly into A at a rate of 400 liters per hour. So that's plus 400. Let me stop for a second. Tell me if this is good. Check everything out. That is going to be, we're going to take into account this influx by just simply accounting for this outflux over here. So we're gonna take account of this inflow just right over here. And X of t is already gonna take that into account. So X of t is taking this into account. Once we actually get this into account, it's gonna be draining that from here and pulling it in. I think it works out. I wondered the same thing, and I convinced myself that this was okay.
Wouldn't it be like plus 500 minus 500 so it equals 0? So it doesn't
Wait,
matter.
there's salt coming out.
There's salt coming out.
Yeah. So we're just focused on the salt flow,
Okay.
not the, we're not keeping track of the pure water, we're just keeping track of the salt change.
So are we saying that the system doesn't lose salt?
No, the system will lose salt through here. We will lose salt. Let me get the Y equation up and then maybe this will feel good. So Y dot, the rate of change in this salt, we've got inflow and we've got a net outflow. And here's where we're going to take account for that 500 that's coming in at this end here. Because there's nothing. There's actually no salt being brought in this way. But there is salt leaving this way. So when we come down here for Y dot, let's do y dot, let me just get my damn equations here and check them out. So this one, tank A, let's do tank A first. There's the current amount of salt, the current concentration of salt in tank A, and that is leaving at 900 per hour into this tank. So it's actually pumping. It's a positive value when we take it from the perspective of tank B. So coming into tank B, this is salt incoming to B. From tank A. And that's why we use X here, because that's the concentration that's determining the amount of salt coming in. And now we've got a loss here. So we're going to have minus the concentration of salt in tank B, and it is leaving at 900 liters per hour. Some of it's going this way. We're assuming a homogeneous mix in here, so whatever's coming out this way and whatever's coming out this way at any instant is the same concentration. So all in all, we're losing 900 from B. And now let's simplify. This is about it. This is all the assumptions taken into account. But the system looks pretty gross, but it's set up, it's a pedagogical example to look really nice. Simplifying, we get and y dot equals 3x minus 3y. And here's our system governing the concentrations in the tanks. And that comes along with this initial condition here. So these are set, this is an initial value problem. So we could go and do the direction field. We're going to take a different tack on this. We could do it just like what I did, but nobody needs to watch me go through that again. Let's talk about a different way to understand this system. Two different ways beyond the things we've already talked about. So, getting a solution. The first method would be a numerical method, and that's what the D-Field app that we've been using does. So a numerical solution essentially involves Euler's method. Unless you want a better one, in which case we're going to open this up to a whole range of Runge-Kutta numerical methods. The simplest of which is Euler's method. Let me give you a sense of just how this would work. I don't want to work the whole damn thing through numerically, certainly not on the board, because our robot friend can do it so much better than I can. But here's the basic idea. We start with our initial condition. So we're going to pick a step size, and this is going to be for time. So we're going to say our change in time is h. I'm just going to use h again because we used that in the past. And we're going to start off with a little table. We're going to say this is our k, that's the step k. This is going to be the current x value, this is going to be the current y value. And I'm probably going to wish those were a little wider in just a second. But at step 0, I know there's 100 grams of salt in tank A and 0 in tank B. So what I'm going to do is use those equations to figure out the rate of change for x and the rate of change for y. And really, you've just got two independent Euler's methods running here. You've got an Euler method for this column, and you're constantly finding the new slope based upon this equation, and you've got an Euler's method for this. However, they are intertwined. So these are coupled, and we just have to make sure that honestly, we don't have to really think about it at all, because we're just gonna plug the current x and y values in here and get the slope that we are traveling in. So my next step at k equals 1, what I'm gonna have here, and I do wish I had made this bigger, is going to be 100, the current value, plus my step size, h, I'm gonna kind of write this out, times negative 3x plus 4/3 y at our current point. So shit. I do wish. I'm gonna make this a whole lot bigger. Sorry, I know it's not as easy for you to fix this up. But I'm gonna have h times negative 3x plus 4/3 y. And this is going to be my step size. So let's say this is 0.1. So I'm gonna use 0.1 for that. My x is going to be 100. And my y is 0. There we go. And I just plug those in here and figure out what that's gonna be. So that is, I'm gonna take a very copious space here. That's 100 plus 0.1 times my x dot change, which is going to be negative 300 plus 4/3 times 0. So that's equal to 100 plus minus 30. And so 70 is my next x concentration. I would probably want a much finer resolution on this. That's a big ass jump. But it's getting a sense of what's happening. And then simultaneously, I'm going to do this y value. It's going to be 0 plus h, my step size, times 3x minus 3y. Again, 0.1, x is 100, and y is 0. So over here, not shockingly, 30 grams of salt just moved to this tank, right? When I simplify this, this is equal to 0 plus 0.1 times 300. And so that's equal to 30. And I'm literally watching the salt flow from tank A to tank B. Too big a step. I would want a much finer resolution. Next step, 2, and I'm not gonna work it through, but it would work out pretty nice, is this next one is going to be current x step plus h times, again, negative 3x plus 4/3 y, but x is 70 and y is 30. And I work that through, and I get the next value. Is this making sense how this would flow? Nope, yeah. And then same thing here. So I'm not gonna ever make you do this by hand. You're welcome. I'm also welcome. I don't wanna look at it. No, I don't wanna make you do it. It's just like bad feelings all around. This is what the app is doing when it's computing the curves. And when you set your step size, this is what you're setting, the delta t. So that's method 1. Method 2 is where the fun starts. And this we will not get done today, but I want to start on it. So method 2 is an analytic approach. Step 2, analytic solution. I just want to note that at level 0 are the D fields sketching. That's qualitative. So that's a qualitative solution. We're just getting the general feel. Numeric is for more precision. This is what you would do in the field. This is what a scientist would do. They would use a better method than Euler's. They would use one of these higher order Runge-Kuttas. If you take numerical methods in the fall, we will do that. An analytic solution is where I actually get a formula. And y of t will equal a formula. So we're going to actually have an equation here that we can plug in any t and know precisely what's happening. But it's also going to reveal things. So this is worth going through. It reveals the hidden structure underneath, the skeleton of the problem at hand. All right, so let's kind of set up. We want to solve x, y dot, so I'm using that notation, that just means x dot y dot in vector form equals a matrix A times x, y. And I've got some initial condition over here, x at 0 is x naught, y at 0 is y naught. This needs to start off with an observation, which is like, it's gonna be a little weird. I'm gonna just tell you, let's just assume this and then we'll see it works. And it'll be satisfying in retrospect if you just forget how I just kind of tossed it out there. Assume we have the eigenvectors and eigenvalues for this matrix A. Let's call this beast A. The eigenvectors, and this is why we did all this stuff, not just to forget. So more precisely, I've got this eigenvector, eigenvalue lambda 1 that corresponds to a vector v11, v12. And then I've got the second eigenvector. Let's assume we have two distinct eigenvectors. And this one corresponds to v21, v22. Value vector. These are non-zero creatures over here. The eigenvalues might be 0. So what I'd like you to notice is this. Well, actually, let's summarize what that means. I.e., if I take the matrix A times v11, v12, I get out lambda 1 times v11, v12. That's the definition of eigenvalue, eigenvector pairs. That if this is an eigenvector for A, and I multiply A by that thing, it's the same thing as just scaling that vector by this factor right here. And we also have that for the second one, v21, v22 equals lambda 2, v21, v22. So we have this. So here's the claim. Claim. X of t, y of t equals e to the lambda 1t. So that's just a e raised to eigenvector times time, eigenvalue times time as its exponent, v1, v2, v11, v12 is a solution to our problem. So this is the part where I'm just like, this is a solution, but I'm going to show you that it's true. How you get there, lots of different ways to understand that. But what's more important is that we see. So to see this, really I'm just going to plug this into that system. So look, here I've got this. I'm going to find the derivative with respect to t of that vector. I'm going to multiply that vector times this matrix A, and I'm going to show that the left side is indeed the right side. So to see this, notice that x dot, y dot, now I'm suppressing the of t again, is, what's the derivative of the right? What is the derivative of this? It's kind of weird because it's a vector, but just don't think too deeply. That's just a constant. What's the derivative of this guy with respect to t? Yes. Lambda 1 e to the lambda 1 t. Derivative of e to something is equal to the derivative of that exponent times e to the f of t. So that's what Lou is using there for that. To take the derivative of this, it's just the derivative of the exponent brought out in front. And then times this vector, v11, v12. This is a scalar. This is a number, and it's times that, and it's times that. So when we put it out in front, you just gotta keep in mind, it's affecting this whole thing. It's literally scaling this direction by some magnitude. So notice that. And then, man, this board got a lot better. When I came in this morning, this board sucked. It didn't work at all. I couldn't erase, but everything seems really good right now. And also, if I take A times this XY, I'm gonna have A times, so let's use, let's put a little bracket. E to the lambda 1t times V11, V12. So that's a little weird. I'm saying A times this vector multiplied by this scalar. And I'm going to use the fact that I can bring this scalar out in front. So this is just a scalar. And it comes out in front. So I'm going to make it E lambda 1t, and then I have A times this vector. Let me write this up and you tell me if that looks reasonable to you. Let me stop. So this is the left-hand side over here. Right now I'm doing the right-hand side of our equation. Make sure to take a good look at that. And then in your mind, what is this equal to? Yeah. That's right. It's this, right? So this, because this is an eigenvector, this is equal to e to the lambda 1t. This thing here is the thing Lou was pointing at, up in the upper left. This is just lambda 1 times that vector. Because eigen stuff. Because of that. So, look, this is the same as this. And that means we have a solution. That's just one of them. I have another eigenvalue and another eigenvector, and I get a second solution from that. So let's write that up here. In a similar way, literally, to see the proof for the other one, replace this one with a 2 and that one with a 2. And it looks exactly the same, and for all the same reasons. So similarly, xy equals e to the lambda 2t times that corresponding eigenvector is a solution. These are the straight line trajectories. These are the straight line solutions. Each one of these, this is just a multiple of a vector. There's some direction, and it's scaled by this factor. Similarly over there. So these are our eigensolutions. They are straight line trajectories that form the skeleton of the flow. And I don't want to draw a general picture with these. We'll do a real one. We'll go to that example with mixing and get those straight line trajectories there. Because this will just start looking like gobbledygook and you'll want to pass out even faster. Right. Let's not do that. Questions at all, friends? That's the theory. There's one last little chunk of theory that I want to tell you, and that is, here's a fact. Again, a fact. It's because of the linearity of matrices. If we have two solutions, x1 and y1 of t, and another solution, x2 of t, y2 of t, if these are solutions to our problem, then any linear combination of those two is also a solution. What does that mean if you haven't had linear algebra? Well, this gives us range to infinitely many solutions that look like this. Then if I take this one times some constant C1 plus this one times some potentially other, probably other constant, is a solution for any constants C1 and C2. This is called the principle of superposition. If you've ever heard that, that's what this is. This is the principle, my God, principle of superposition, which just sounds really cool, but it just means linear combinations of solutions or solutions again. All right, to find these C1 and C2, so the way this flow is going to go, let me show you the plan before we even do it. The plan is going to be this. Here's the step-by-step plan. To get an analytic solution to xy dot equals a x y, so a times xy with some initial condition. Step one, everything comes down to the eigenvectors and values. Find the eigenstuffs for A. Let's say that's lambda 1 and vector 1, lambda 2 and vector. This is a double-headed arrow I'm just using to, in my own notation when I'm doing this, I use this arrow to just keep things organized. That means this goes with this vector, vice versa. Step one is that. Step two, write the general solution. And the general solution is going to look like this. X of t, y of t equals C1 times e to the lambda 1 t v1 plus C2 e to the lambda 2 t v2. Step three is find C1 and C2 to make the initial conditions true. Use the initial conditions to find C1 and C2. So let's knock out that problem and call it a day. So that equation that we had, back to our mixing problem, x dot equals negative 3x plus 4/3 y, y dot equals 3x minus 3y. I think I got that right. Let me slow down to see if people still right. Wish I had my T. It would help me slow down. I do have these awesome Twizzlers still. Almost gone. All right, step one, turn this in. I guess there's a step 0, which is write as a matrix. So xy dotted equals, what is the matrix? Just copy the coefficients. This is A. Here's your chance to see how much you remember. Please find the eigenvalues of A. And then, of course, do the vectors, whatever else you can summon up. Remember, this this eigenstuff starts with the values, and you're going to use this form of the characteristic polynomial for lambda. Lambda squared minus the trace of a times lambda plus the determinant of a equals 0. This one works out beautifully. This is a really sweet problem. Totally snagged it from the book. Should be nice. And I will supply the vectors because I already worked this one through, so we'll save ourselves some time. And come around. Emotional support. Did you get caught up? Okay. Like, did you get a chance?
I need to watch a little bit of like the ends of both of them and like do that.
Yeah, I was looking at the average viewing time on that video was 10 minutes.
Yeah,
but,
busier weekend.
no, fair
than I was
enough. No,
hoping
no
for.
harassment even intended slightly.
Yeah, I have time today, so I'll be watching
Thank
them.
you. Yeah, it'll help. It'll definitely be good. And then I started looking at the average viewing time on a lot of my videos. A lot of them are 10 minutes. It's just like, what do people, well, you guys aren't even watching them. Somebody else is.
It's funny.
So, I don't know what's happening. Just sanity check on that characteristic polynomial. Which really factors like a dream. And I'll kind of start writing up some of the next stuff here, because I did find these vectors. Which, if you're having trouble if you're having trouble with any of this, we should talk. But you could check yourself to make sure that you're getting how to do these. These are just multiples of some less nice ones. I mean, I just picked the nice version, 30. And then once you've got that, we can just literally crank out the solution. First you write your general. And I want to write out what that means because I feel like there's probably a couple folks who are like looking at that, but not 100% sure what that means. And it just means two different equations, row separated. So this one's going to be 2c1 e to the, so I'm just grabbing the x components, e to the negative t minus 2c2 e to the negative 5t. And then the y flow, the y concentration is governed by 3c1 e to the negative t plus 3c2 e to the negative 5t. And if I do that initial condition, x at 0 is 100, y at 0 is 0,
when you plug these in, the equations are gonna look like this. So 100 will equal, replace the t with 0, it just kills the e's. So you get 2c1 minus 2c2. And this one's 3c1 plus 3c2. Is that right? Yeah. So I guess I have to solve this system then, which is starting to sound less appealing. Let me see if I did the work already. I'm super lazy about solving that. Oh, I didn't. What up? I'm not gonna call myself names anymore in front of anybody.
Good.
That's right, isn't it? Yeah, that was the thing I was most upset about, that I got so hard on myself. It's like, shit happens, right? Oh, gosh. Can anybody solve that in their head?
Would you be able to just know that C1 and C2 are opposites of each other? And then you
Cool.
just need 4 of that?
I love that. That's great. So this says, this second equation says C1 equals negative C2. So if I plug that in, yeah, that sounds great. So this top one, if you replace C2 with negative C1, that's 4C1. So C1 equals 25, C2 equals negative 25. Thank you. Sweet. So we've got, oh my God, we've got a solution. Let's write it up. Got time, even got minutes left. X of t equals, C1 is 25, C2 is negative 25, so it's gonna be 50 e to the negative t plus 50 e to the negative 5t. Which makes total sense because at time 0, then we've got our 100 grams in there. And as time moves positive, these e's are gonna shrink to 0. So you'll see that concentration drop. Erstwhile, the y concentration should rise and then drop. So let's see, we're gonna have 75 e to the negative t, and then minus 75 e to the negative 5t. I'm gonna get the computer up so we can just take a look at this and call it a day. That was a good day. So that assignment that I probably said it was due Wednesday. That sounds like me. Let's make it due Friday. So if you haven't started it, please start it before Wednesday and we can talk. And I will pull this back down if you're still taking notes, I understand. But let's take a look at our system. That guy, I'm gonna enter that, and let's see, so that is negative 3x. And since these are concentrations, the only part of the plane that really matters is the first quadrant. But we'll just take a look at the whole. I guess I don't even need the times, that'll probably screw it up. And then this one was 3x minus 3y. And here we go. So, just a couple of things to point out here. Be gone, whatever you are. Wait, why is it showing me that? I don't know. Doesn't really matter. I didn't enter an A, did I? No. Let's clear the graph. Cool. And then you can see the straight line trajectories kind of like right there. Oh boy, yeah. That's the money shot right there. And then there's another one that comes in here, but I have to like kind of, if I looked at that vector, that was the eigenvector, which I think was negative 2, 3 or some multiple thereof. But down here, here's our problem. Like we started with something in x and nothing in y. So imagine this is 100 here, this is the X concentration, continually decreasing the amount of salt in tank X, and the salt in tank Y starts to rise up, and then decreases to 0, and eventually everybody's just flush with water. Yeah? I had a good time. Hope you did. Yeah, Lou?
Is this like blood transfer, like, applications here?
Maybe. Sure. Yeah. I don't know. I don't know enough about biology to even intelligently, and I'm a little squeamish about blood. Thank you. Thanks.
Because we have stuff.
You doing alright? I saw you biking like yesterday.
What were you saying?
There's like
See you in a minute.
lots of
Yeah.
stuff in your blood.
Like a lot. Yeah, that's all I was.
It probably works like this. I bet it's a lot more complicated though, just because like stuff
Yeah.
comes like dissipates through the arteries and veins too, right? Doesn't stuff like pass through those blood?
Yeah.
Barrier.
It's not the practice.
There's like
It all makes sense. What I
Plus, like, you're constantly metabolizing.
yeah. Yeah. Good.
I did do that, and
Good. Good.
I went over it.
Okay. Thank you. Good. This makes me happy.
Me too.
Yeah. This is essential.
Yes, it
Yeah. We gotta like.
is. Ramp
Yep.
up.
But it, like, is this making sense? This is kind of like a fresh start in a way. So
I mean,
there's less calculus for sure.
I think that it's kind of confusing with like where you got the E specifically.
Yeah, I understand that because I kind of just pulled it out of my notes. Yeah.
But like I know how to find
So might as well just get
Eigen stuff.
That's good, but that's what
As long as you can do the Eigen stuff,
Yeah.
that's the core mechanic.
Yeah, that's fun.
I like it too.
Yeah.
I like it too. Cool. Thank you.
Thank you.
All right. Thank you.
See you later.
Good stuff. See you later. Sorry, I stink.
I have the
Hi.
modern geometry homework.
Oh, beautiful.
And
Thank
I
you.
also have a doctor's appointment today. They were only open Monday.
Oh, sure you do, Tara.
I can get you a note
I
if
just
you
don't
want
like
it.
coming to class.
No,
No, I'm
really
kidding.
not loving watching
No, I-
videos all
No,
day,
I'm
but
sure it sucks.
I'll catch up today and get the
Let me know
other
if you need to
tomorrow.
meet or if you need me talking,
Okay.
and we can do that.
Okay, I'll let you know after today how
Sounds
it's
good,
sitting.
friend. All right,
Thank
thanks.
you.
I got the homework. I'm not sure. Is that it? Is that all I'm supposed to do? Or
Um,
is there more I have to do?
No, I want these are
Ugly.
these are pretty ugly.
Okay.
Yes.
I'll make them bigger.
So I also want to see these null lines on here. I'm not seeing. It's not obvious. Make more detail. Make these obvious.
Okay.
Okay.
Do more
And
labeling
more
and make it
arrows.
bigger and, like-
Yeah, I want this to look much more like what I had
Okay.
up there.
I can
Does
do
that sound
that.
good? But you
Yeah.
had a good start.
Okay.
Yeah, refine. Refine now, Tracy.
Yeah, that's fine. I just wanted to make sure.
I probably know who's the other people watching the videos, because I'm not gonna lie, I sent your YouTube channel to a couple of my friends I've seen in Denver, because they say they're, because I showed them our textbook, right, for calculus,
Yeah.
and they said their textbook is complete ass compared to ours.
Oh God.
And
okay.
then when I took your Calc 2 class, even though I wasn't
You
in,
should take this off the video. Show. Yeah.
no, even though I didn't like show up